Okay, one more thing I want to talk about is creating stacks. This is tidy model stacking. This package is used to create ensembles of models. Okay, and basically, uh, what it does is, or what you do is you create these different models. Okay, and each of these models, make different kind of predictions, and then you combine them all into like one kind of super like Voltron model, a model that's like made out of these other models. This is an ensemble, okay? And I will say this is probably one of the more powerful packages. And in years past, in past iterations of 101C, the winning teams all used stacks or ensembles of models to do their thing. So I think you will get kind of better performance if you combine several models through a stack. And so I want to kind of walk through just kind of the ideas of how this works, and then we'll work through the kind of reference article of getting started. And so I'm just working through the documentation, and I'll just read through the documentation here, but I think that it will be kind of a good explanation for how this goes, okay? So the way stacks work is the process goes like this. You're going to define your different ensemble members. So those are just individual models, and you're going to do that kind of just with the techniques you already know. So you're going to use parsnip to define a model. You'll create a recipe. You'll set up a workflow, maybe tune these things, and rsample, to create your kind of v-fold cross validation to do that. All right. Then you'll create a data stack. All right, and that's done using the stack function. And as you work through them, you're going to add each of these kind of candidate members using add a candidate. Okay, and once you've finished adding these different candidate members, you're going to combine their predictions, okay, using blend predictions. All right, and then you'll fit once you blend the predictions. Okay, what blend predictions will do is it will figure out like how much each of these candidate members should be weighted. Okay, and some of them are going to get weighted 0, meaning like this is not a very good candidate member model, not a very good kind of model, so we're going to just kind of throw it out. But anyway, once you do that, you'll click fit members, and then finally you'll ask it to make predictions. Okay, so if it's not already in there, you'll install it using install.packages. Okay, Stacks is generalized and can kind of work for all kinds of different model types, and it will basically work for anything, any kind of cross-validation scheme that you need. Basically, we can just kind of stick to regular old cross-validation, but if you have something fine-tuned, as long as you're using rsample to do it, it will work. And then as far as measuring your performance, just use whatever you have in Yardstick. Yardstick kind of are the different metrics we have, RMSE, or if you want to use the accuracy metric, or whatever metric you want to do. Okay, and then the way it combines them is it just uses a regularized linear model. So it kind of, you just multiply it by some kind of each of the models themselves get multiplied by some kind of coefficient, and then they get added together, and that ends up doing a pretty good job. Okay, and so here we'll start with kind of this conceptual explanation of how it works, and then we will work through the I guess tutorial example here. Okay, and so it says at the highest level, ensembles are formed from model definitions. Okay, in this package, model definitions are an instance of a minimal workflow which contains a model specification. So you say, I want to create a linear regression model, or I want to create a random forest model, whatever you do with parsnip. Okay, and then if you have a recipe, that goes in as a preprocessor, right? And optionally a preprocessor. And So the model definitions specify the form of candidate ensemble members. And so this kind of example, they're saying, okay, we have a KNN model, a linear regression model, and a support vector machine model. Okay, so it says a diagram representing model definitions which specify the form of candidate ensemble members. And we have KNN in salmon color, linear regression in yellow, support vector machine in green. Okay. To be used in the same ensemble, each of these model definitions must share the same resample. So basically, if you've set up some kind of like v-fold cross-validation, that's going to be your resample. So you use R sample to do that. You use v-fold cross-validation or some other kind of sampling object you have. That's what we have. Okay. And so when paired with the model definitions, that's how we're going to generate the tuning and fitting. Do the tuning and fitting results here. Okay. As far as our KNN model, we might have different kinds of KNN models with different hyperparameters. So this says we have candidate members generated from each of our model definitions. So we have 4 KNN things with different hyperparameters. So this might be a KNN where we're using 5 nearest neighbors, and this one might have 10 nearest neighbors, and this might have 15 nearest neighbors, and this might have 17, whatever, right? We've got 4 different KNN members. Here, I guess we just have 1 linear model member. That will just be LM1. And then our support vector machine model, apparently we have 6 different models available to us, all right? So it could be, support vector machine with this gamma level or this kind of cost parameter, whatever it might be, right? So the support vector machine, you've got different parameters, and apparently we have 6 of these different things. And what we'll do is all of these different candidate members are created in a stack. We call this a data stack, and we add each of these things using add candidates. So we say add candidate KNN1, add candidate KNN2, so on and so forth. We add all of these up, okay? Each of these objects themselves, internally, the way tidymodels stores them are tibbles, okay? Where the kind of first column gives kind of the true outcome in the assessment set. So you have your v-fold cross-validation, it's fit, and then it's evaluated, okay? And the remaining columns give the predictions from each of these candidate ensemble members. So we have the true value from the assessment, for the test cases, we have the true, and then we also have the prediction. And that's how Stacks evaluates the performance, okay? So when the outcome's numeric, there's basically just one kind of column for the prediction, but if it's classification, you'll get, kind of multiple things for the different levels. Okay, so anyway, this is created in our data stack, okay? And so we have the true outcome, and then we have the predictions made by KNN1, we have the predictions made by KNN2, the predictions made by KNN3, so on and so forth, okay? So each of these columns correspond to the different kinds of predictions each of these models are making. And this is how the package Stacks is going to evaluate, like, here's the true value, and, this is what this guy thinks the predictions are, and this is what this one thinks that the predictions are. And this is how we try to evaluate, like, okay, how do we compare all of these at the same time, okay? So this diagram represents a data stack, which is a special kind of data frame. And the colored columns depict the in white, the true value of the outcome variable in the validation set, followed by the predictions made by KNN, the predictions made by the linear regression, and the predictions made by SVM, okay? And then we use this function blend predictions to say, like, okay, what's the best way to kind of combine these different things to get as close as we can to the outcome variable, okay? And so that process, right? So these are all predictions, and ideally each of these predictions are like kind of close to the outcome variable, but they're all going to also be a little bit different from each other, right? And so this kind of thing of like, um, this one makes certain predictions, and this one makes different predictions, and this one makes different predictions. They get blended together, and we call that process kind of meta learning. Okay, it says outputs of each member are likely to be highly correlated, which we expect, right? They're all making predictions. They're all trying to predict the same thing. None of them do it perfectly, but they're also going to be kind of highly correlated. And so it says, thus, depending on the degree of regularization you choose, the coefficients for the inputs, for of possibly many of these outputs will end up being 0, right? So, in this example, it said, Canaan 2, 3, and 4, these models, they got 0 coefficients. So basically, these models just don't get factored in to the final output. So they're just kind of thrown out. And it says, we're going to weight KNN1 this much, and LM1 this much, and SV2 this much, and 4, 5, 6, all of these different. So you get these different kind of stacking coefficients for each of these things, okay? And then the coefficients are used to say, like, okay, we're going to multiply each of our predictions kind of by this factor and then blend them together, okay? And that's what we have. So it says the coefficients of the linear model combining each of these candidate model predictions to generate the ensemble's ultimate prediction. So we use, these, I guess, 6 models together with their coefficients. They get blended together. Okay, boxes for each of the candidate members are placed besides each other, filled in with the color, so that's just what this is, right? So these are the fitted candidates, and that's what we do. So it says a diagram representing the model stacks class, which is what we have, which collates the stacking coefficients in members, okay? And then and the members are the things that don't have 0 coefficients. And then the representation of the stacking coefficient is as before, where the members are colored in pentagons are listed as subclass, all right? And then finally, the model stack object that we have is ready to make predictions on the new data, okay? And so that's what we end up having, okay? So let's just kind of walk through this process. Through this, we'll just kind of follow along the tutorial. And again, all you have to do to access this is you go to tidymodels and then find stacks, and then go to the under articles, getting started with stacks, okay? And you have additional articles for classification models and whatnot, but this is the one that we will work through, okay? So again, the workflow is define the different candidate ensemble members. So these are your individual models that you might want to try to combine together. You create a stack object, data stack object with stacks, add the members themselves, combine their predictions with blend predictions, and then fit them, and then make new predictions. Okay, so we're going to use a data set called tree frogs, which I guess gave experimental results on hatching behavior of tree frog embryos. Okay, so it said the red-eyed tree frog embryos can hatch earlier than their normal 7 days if they detect potential predator threat. Okay, researchers want to determine how and when these tree frog embryos were able to detect stimulus from their environment. So they subjected the embryos at varying development stages to, quote, predator stimulus by jiggling the embryos with a blunt probe. So they took these things and they kind of were poking at them or jiggling them. And it said beforehand, though some of the embryos were treated with gentamicin, whatever, I don't know, a compound. I guess some of them were treated with some kind of compound that knocks out a sensory organ, their lateral line, okay? And it says researcher Julie Jung and their crew found that these factors inform whether an embryo hatches prematurely or not, okay? So here the variable we're going to try to predict is called latency. That's basically the time to hatch. And we're going to look at can we predict that based on the other attributes. And it says we'll need to filter out NAs. Those are cases where the embryos did not hatch first. So we'll load up our data. We take our data. We're going to say filter anything basically remove anything that's NA, right? So we filter only keep the things that are not NA, okay, for latency. And then we'll also get rid of the variables clutch and hatched, okay? Okay, so if we just take a quick look at the data, it says hatch time is pretty closely related to some of our predictors. So here, this is just kind of a plot as far as embryo age and time to hatch. Okay, so here we've plotted how old the embryo is and how long the time it took to hatch. And then I guess we have the control, and then those that were treated with gentamicin and yeah, okay. So let's see. This is again the at varying development stages. So when they were I guess the age, embryo's age at the when it was stimulated or something. Okay, so here we're going to specify our different candidate models, and we'll have a KNN model, a linear regression model, and a support vector machine model here. Okay, so we'll set up our kind of workflow. So it says defining the constituent model definitions is undoubtedly the longest part of building an ensemble with stacks, okay? And it says if you're familiar with tidymodels proper, you're probably fine skipping this section, but keep a few things in mind. So you'll need to save the assessment set predictions and workflow utilized if you ever did like tune grid or tune bays. We haven't talked about that yet, but you know, tuning grid to kind of pick your hyperparameters, fit resamples, if you did that, you know. So probably a lot of you, I imagine, will use tune grid to figure out which of these, you know, what is the right set of hyperparameters to use, okay? And so when you do that, you'll want to choose the option save predictions equal to true, and also save workflow to equal true, okay? All right, and then and you have to use the same kind of v-fold cross-validation, which is a type of RSet object. So you can't do one v-fold cross-validation and use like a different v-fold cross-validation. Sometimes you want to check if, because v-fold cross-validation is subject to randomness, you might want to run it multiple times, but if you're going to run it multiple times, you're going to have to run your stack multiple times as well. Okay, so it does get computationally expensive. Okay, so here we're going to set this up just kind of, we take our full data, we do our initial split between train and test. Once we have our training data, we'll do v-fold cross-validation. That's going to be set up our fold, and then we're going to have the basic recipe is just like throw in all of the variables, okay? So that's just basically our thing, and then our evaluation metric is going to be RMSE. All right, so this is just very kind of basic, sets up our set for the resampling, which is 5-fold cross-validation, and we're going to just have a very simple recipe, just predict latency based on all the other variables. Okay. It says tuning and fitting results for use in ensembles need to be fitted with the control arguments, save predictions, and save workflow. So if you do something like tune grid, make sure you use these options. It says these settings assure that the assessment set predictions as well as the workflow are stored in the resulting object. It says for convenience, stacks supply some control stack functions to generate the appropriate objects for you. Okay. So it says here we'll be working with tune grid and fit resamples from the tune package. So we'll use the following control settings: control grid and control resamples. Control stack grid and control stack resamples will kind of automatically set these settings for you. Okay, so that you don't, when you do tune grid, you don't have to manually type all of these things yourself, okay? And it says we'll define 3 different model definitions to try to predict time to hatch. We'll use a k-nearest neighbors model, a linear model, and a support vector machine model, okay? For k-nearest neighbors model, we have hyperparameters to tune, and support vector machine also has hyperparameters to tune, and we'll use tune grid to figure out those hyperparameters. So we begin by creating a parsnip model. So this will be, this is going to be our KNN model. We'll say I want basically a k nearest neighbors. We're doing regression, and then we want to figure out what is the k that we're going to use, okay? And so we're going to set that to be a tunable parameter that we'll refer to as k. So that's going to be my k nearest neighbors thing, okay? It says note that since we're tuning over several possible numbers of neighbors, this model defines multiple model configurations, okay? The specific form of those configurations will be determined when we specify, in the grid search doing tune grid, okay? Here it says we extend the basic recipe definition defined to fully specify the form of the design for the k-nearest neighbors. So for k-nearest neighbors, we have to extend our recipe by kind of taking all of our nominal predictors and making them dummy variables. We're going to get rid of anything that has 0 variance. If we have missing values, we will impute the mean, okay? And then all of our numeric things we will normalize, okay, so that they have mean 0 and standard deviation 1. So we extend our recipe, so we have a k-nearest neighbors recipe, and we add these steps here. So it says, starting with the basic recipe, we convert categorical variables to dummy variables, remove columns with only one observation, impute missing values in numeric variables using the mean, and normalize numeric predictors, okay? Pre-processing instructions for the other models are defined similarly. We're going to combine the model specification and the pre-processing instructions into a workflow object. So we say workflow, add the model, the KNN model, add the KNN recipe. That's going to be our KNN workflow. So that's our KNN workflow. Okay. So far, I think this is all very familiar, right? This is how we specify things. And then, so now what we want to do is we want to try out different hyperparameters as far as my tunable parameter k, and we're going to use that using tune grid. It says finally we make use of the workflow, the training set resamples, the metric set, and the control object to tune our hyperparameters. So using the grid argument, we specify that we want to optimize over 4 possible values of k using a grid search. So I'm going to say take my KNN workflow. We'll use the v-fold cross-validation, the RMSE metric. I want to have 4 possible values to test out for tunable parameters thing. And then as far as the control, in order that we save our the workflow and whatever, okay, we have control grid. Control stack grid is kind of some, has some presets that will make this easier, okay? So, so I say tune grid, and I say store the results in KNN results, okay? And so the KNN results are the result of doing, running the tuning grid on 5-fold cross-validation. So it has all of the kinds of different folds and all of their different results, okay? It says this KNN results object fully specifies the candidate members and is ready to be included in the stacks workflow. All right, and it says, so we're going to do similar kinds of stuff for the linear model. Okay, here we have no hyperparameters to optimize, so we're just going to fit it to the v-fold cross-validation, and so we'll just do fit resamples rather than doing tune grid or tune Bayes or something like that. So here I'm going to specify linear regression just using LM. The recipe takes my basic recipe, and I'm also going to do make dummy variables and also remove any 0 variance predictors. Okay, we'll create our workflow, which we add our model and I add our recipe. And then here I don't have anything to tune, so I'm going to call fit resamples. Okay, I use the v-fold cross-validation. I want to evaluate on RMSE. control resamples, make sure as I'm going to store the results needed to do stacks. Okay, and so these are the linear regression results. That's what we have here. Okay, and then as far as SVM, I do similar kind of thing. I define my model. I have two tunable parameters. I have the cost, and I have the sigma for the basically my gamma value for the radial basis function. Okay, what is the sigma there? So I've got two parameters to kind of mess around with. We'll use the kern lab for powering the SVM, and then we will again extend my recipe. I want to make dummy variables, remove the zero variance, get rid of fill in missing values with the mean. We'll also have a correlation filter there, okay, and normalize our predictor. So that's my recipe. I add that recipe to the workflow, okay, and then here, because I have parameters to mess around with, I'm going to set up, I'm going to call tune grid to try to identify what set of parameters to use here. So I call tune grid. I'm going to say grid equals 6. And again, all of these things do take a little bit of time to do. And then the results, I have my SVM results. Okay, and so again, using control equals control grid, which we specified using control stack and things that has the settings. So this stores all of this. So here I've got 4 KNN members, 1 linear regression candidate model, and then I have 6 SVM support vector machine models here. Okay, and so we want to stack these different model configurations. Okay, and it says, note that in most applied settings, one would likely specify many more than 11 candidate members. So here, just in this example, we have 11 candidate members. But when you do your thing, again, the more members you have, the more computationally expensive it becomes, and it takes your computer a while to fit all of these things. But you might have a whole bunch of models included in your stack. Okay, so now what we want to do is we want to build our stack and then blend our predictions. So here we're going to just initialize a stack by calling stacks. Okay, so this creates a empty data stack, 0 model definition, 0 candidate members, but we're going to add all of our different 11 members here. Okay, so the stacks function works kind of like the ggplot constructor in that you just kind of keep piping in all of these things. Okay, so our stack is going to be, okay, tree frog stack. We're going to call stacks. We're going to add candidates, KNN results. So KNN results already has all of the results. Our metrics, it's 4 by 5. We have four models, okay? 4 models stored in here, okay? And then the predictions are all stored in there as well, okay? So I say, hey, add my KNN results, add my linear regression results, add my SVM results. And again, the SVM, there's 6 models in there. The linear regression, there's just 1 model. So I just say, hey, add the candidates, add the candidates, add the candidates, all right? And it says, yeah, you have 3 model definitions and a total of 11 candidate members, okay? The KNN has 4 model configurations. The linear regression has 1 model. SVM has 6 model configurations. So this forms my tree frogs data stack, okay? A data stack is just a tibble with a whole bunch of attributes. So you can ask as tibble on this, and you can see you have the true value along with basically the predictions made by each of these things. Okay, some of them didn't do a really great job, but basically it says the first column gives the first response value, and the remaining columns give the basically the predictions from each of these ensembles. Okay, so when the true value was 79, KNN predicted 74, this one predicted 71, this predicted 64.2, this one predicted 63.9, this one predicted 78.6. That one did kind of good. And this one, when it was 50, it was kind of all over the place. None of these seem to do a really great job. But anyway, we're going to try to evaluate this. Look at this one. This one, the actual value is 52, but we predicted all kinds of values. So anyway, we have basically all of these things in the regression case. In the classification setting, there's going to have a whole bunch of more columns, but that's it. Okay, so this is how we've created the stack, and so now we want to figure out how to blend these predictions. So the outputs from each of these candidate ensemble members are highly correlated, so we're going to do blend predictions. That's going to perform regularization to figure out how we can combine the outputs from the stack members to kind of come up with our final prediction. So you just take your tree models stack, which we called tree frogs data stack. Tree frogs data stack we call blend predictions. And when it's done, blend predictions determines how the member model's output will ultimately be combined in the final model. And some of these things end up with 0 coefficients, others have other things, and so that's what we have. So it says to make sure that we have the right trade-off between minimizing the number of members and optimizing performance, we can use an auto plot. So yeah, in general, you don't want to have too many members, but also you want to have good performance, so we can call auto plot, and this is what we have: number of members, and the RMSE and the R squared, so we can see our RMSE goes up, and so anyway, so this is says to show the relationship more directly, average number of members type E is equal to members. It says, if these results were not good enough, blend predictions could be called again with different values of penalty. As it is, blend predictions picks the penalty parameter with numerically optimal results. And so these end up getting kind of our stacking coefficients. All right, so anyway, now that we know how to combine our model output, we can fit the candidates with non-zero stacks. So remember, so here we're going to say we take our data we call blend predictions, and this will create our model stack. And now that we have our model stack, we call fit members, right? And so that's gonna it says can be thought of as a group of fitted member models and a set of instructions on how to combine their predictions. So that's what we end up getting. You can collect parameters, and it will give you kind of the corresponding parameters for each of these things to identify which model configurations were assigned what stacking coefficients. You can call this, and it will say, the SVM thing was this, and its resulting coefficient was this, or whatever. So that's what we have. And now that we have our stack, we can then call predictions. So we'll take our test data, and then we'll say make predictions using our trained stack. And we can kind of plot this, all right? And it says, how good is our predictions versus the actual. So the actual values were this, and these are the predictions. Perfect predictions would end up in a straight line. I think it's kind of tough to predict these. It says, looks like our predictions were pretty strong. How did the stack predictions perform, though, as compared to member predictions? We can use the type equals members to generate predictions from each of our ensemble members, and so we can see, the RMSE from each of these things. These are the kind of root mean squared error values for that. Do we have root mean squared errors for the entire stack? So our stack, our dot prediction, was 54.3 when all combined. Individually, our RMSE was 56.1, 55.5, 56.9, or 60.6. So indeed, when we combine the stack, we get our best performance here. I think these values are kind of tough to predict in the first place. But yeah, individually, each of these models themselves had not as great as performance compared to the predictions as made by the stack. Okay, so it says, as we can see, the stacked ensemble outperforms each of the member models, though it is closely followed by one of its members. So we have 54.3, outperforms the linear regression model a little bit, but it's not drastically so. Okay, but anyway, this is how you would go about using a stack, and I think it's a very powerful tool. And I will say that in the past, all of the winning models ended up using a stack. So definitely try it out, and that's an option that's available for you. Okay.